All right, so hello everyone. Thanks for taking the time to watch. Welcome to our week 5 Poliventure. Recall that Poliventure is a workshop that explores how games relate to concepts in political science. So I'll be live streaming games like Catan Universe, Risk Board Game, and Sid Meier's Civilization, and discussing how different elements of the game relate to political science. Now, note that from our other weeks, we've had an overview, risk, network, settlers of Catan, and now we're on randomness and probability. And then in future weeks, you'll see signals and bluffs, and then real world applications 1 and 2. So let's go ahead and jump to week 5, randomness and probability. And the learning objectives for this workshop are the following. First is to define randomness and probability. Secondly is to explain how randomness and probability are related, and then apply randomness and probability to the game of Catan Universe. So with this, let's add a 6th concept. We start off with 4. So the first 4 were communication, information, strategy, and moves. And then we added network, and now we're adding probability. And note that there's 2 types, or we can say 2 values of probability we'll look at is high and low. So first, let's start off with the question of what is randomness, right? So randomness is the apparent or actual lack of a pattern or predictability in events. For example, random sequence of events, symbols, or steps often has no order and does not follow an intelligible pattern or combination. And individual random events are by definition unpredictable, right? But if the probability distribution is known, the frequency of different outcomes are repeated over repeated events is predictable. So for example, throwing 2 dice, the outcome of any particular roll is unpredictable, but a sum of 7 will tend to occur twice as often as a sum of 4. In this view, randomness is not haphazardness, right? It's the measure of uncertainty of an outcome. Note that randomness applies to concepts of chance, probability, and information entropy. And obviously you can learn more by checking out the Wikipedia entry. Most of the times when we think of randomness, we're like, oh, that was random, right? Like somebody running a red light, and you're like, that's random. Or some kind of event happening that wasn't expected or is very unlikely, and you're like, that was random. Or when somebody says something in a conversation that wasn't a part of the conversation, like that was random. So we had this idea of random in our mind, but what we're going to try to do is fix it a little bit and then attach it to the concept of probability. So what is probability? Right. So probability is the branch of mathematics concerning numerical descriptions of how likely an event is to occur or how likely it is that a proposition is true. The probability of an event is a number between 0 and 1, where roughly speaking, 0 indicates the impossibility of the event, while 1 indicates the certainty of the event. So when we think of probability, we're working with a number most of the times greater than 0 and less than 1, somewhere in that middle world, because anything that is impossible to happen, it's not probabilistic. We're not interested in it in a probability sense. And if it's certain to happen, then it's also, in a sense, not of interest to us because it's not probabilistic. So this next idea is the probability distribution. If you've taken a Math 160 or Sci 215 or other types of statistics course, you probably heard of probability distribution. So let's just introduce it again for those who may have not taken those courses yet. So in probability theory and statistics, a probability distribution is the mathematical function that gives the probabilities of occurrence of different possible outcomes for an experiment. When we say experiment here, we're basically saying a dice roll or some other kind of probabilistic object that we put out there to see what's going on. So like a roulette table, deck of cards that you draw a random card from, etc. It is a mathematical description of a random phenomenon in terms of its sample space and probabilities of events or subsets of the sample space. So for instance, or for example, if X is used to denote the outcome of a coin toss, the experiment, then the probability distribution of X would take on a value of 0.5 or 1 in 2 or half, right? So for X equals heads, that's half. And if X equals tails, that's also half, right? And we're obviously assuming that the coin is fair, so it's not weighted one way or the other. So flipping a coin is an example of an experiment where you're trying to denote the probability of either a heads or tails occurring. And what we should see over the long run, so we flip it multiple times, let's say hundreds of thousands of times, we should see that about 50% of the flips land on heads and 50% of the flips land on tails. Now let's see an illustration of this. So if we had a single dice, right, we know a dice has 6 sides, and we can see probability represented in 2 ways. On the left-hand panel, you'll see that PR parenthesis X equals little x, close parenthesis equals, and then here's the different types or ranges of probability. So 1/6 chance that you'll roll a 1, a 1/6 chance that you'll roll a 2, a 1/6 chance that you'll roll a 3, a 1/6 chance that you would roll a 4, a 1/6 chance that you would roll a 5, and a 1/6 chance that you would roll a 6. In other words, if you have a dice, right, and you roll it, there's a 1/6 chance that any one of those 6 numbers will come up in a single die roll. A visual way of looking at this is this rudimentary drawing, and you'll see that the probability of any of these numbers is about 16.67% chance of showing up after you roll the dice. That's also equal to 1/6 of a chance, right? So 1/6 of a chance is equal to 16.67% of a chance. Now, what's interesting here is that if we ask ourselves, what's the probability of rolling a 1 or a 2 when we roll a dice? Well, we just add up those two probabilities. In this case, 16.67 plus 16.67 equals 33.33. So we have a 1/3 chance of rolling a 1 or a 2, or a 33% chance of rolling a 1 or 2 when we throw a dice. Now, this is just a single event, right? A single dice rolling it once, and these are the chances that we get of rolling a particular number. Now, what we're interested in is the probability distribution of all the numbers that we can collect over time. But before we do that, what I'd like to just point out, like, imagine instead of having just one dice, now we have 2, right? So what's the probability represented in 2 different ways? On the left-hand side, you'll see what the total number is, right? So if we roll 2 dice, there is one way of getting the number 2. So if you roll a 1 and a 1, right, that's 2, and you have a 2.78 probability of getting a 2. Now, if you roll 2 dice again, there's 2 ways to get the number 3, right? In this case, it'd be like, so say you roll your first dice and that's a 1, you roll the second dice, that's a 2, that equals 3. Or the reverse could be you roll a 2 and then a 1, that's also a 3. You have a 5.56% chance of rolling a 3 with 2 dice. Now you'll start to see that what we're doing is, as we get to those middle numbers, 6, 7, 8, the probability of rolling them gets higher. So for example, 6, 7, and 8, they have a probability of, there's 5 combinations that you can roll of 2 dice to get 13.89%, 6 combinations of rolling 7, which gets you 16.67%, and then 5 combinations of rolling an 8, which gets you 13.89%. So what you'll see is, like, 7 is the most common number that you would roll if you were rolling 2 dice that were fair. Now you'll start to ask, well, why does it go up and then why does it go down? And let me just draw on this really quick so you can see what I'm talking about. We go up and then we start to go down. You might be asking, well, why that's the case? Well, for example, for the number 12, there's only one combination that you can roll in order to get to 12, right? So give yourself a second to think about it. Recall that there's only one combination that you could roll to get a 2. And remember that you have, in order to get a 2, you have to roll your first dice as a 1 and your second dice as a 1, right? So 1 plus 1 is 2. Now, which 2 die numbers would you need to roll in order to get a 12? So we'll do ding, 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 da, 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 da. And now you'd have to, your first dice would have to be a 6 and your second dice would have to be a 6 because 6 plus 6 equals 12, right? And the chance of you rolling that is 2.78%. So in this case, what you'll see is that this begins to generate a distribution of what's possible with respect to combinations of die roll. So what we're going to do now next is apply this idea of randomness and probability to the game of Catan Universe. So I'm going to go ahead and pause it for a moment just to get this set up, and then we'll go ahead and walk through that process. All right, so I've gotten the game set up, and what we're going to do here is see a screenshot of the game, right? So I open Catan Universe, and I'm going to choose the game here, and scenario is my first option. And then from there, I get 4 choices of scenarios, and I'm going to choose the one called First Island and then click New Game. So I've done that. And then next, I'll go ahead and configure this scenario. And in this case, it's asking me what's the victory point. So I'll say 10. Is there a timer on? No. So it's off. Random player starts. Yes. Right. Which means that the players, there's 4 of us. The order in which we start will be randomly determined by the computer. In other words, the computer is going to roll a dice for each of us, or flip a coin for each of us, saying, you know, let's see what the order they get, or a 4-sided die, which would be kind of difficult to have, but possible. We'll turn off the friendly robber, which is basically a component of the game where some non-player controlled entity is able to go around and steal resources from you. The dice mode will not be on card stack, and then we'll have a random map. So imagine that there's all these tiles with different resource on it, and then they're randomly put into some particular order. And now we have our first round and our map generated. So let me go ahead and switch over to the game. And let me check something really quick. Have the audio set up. Let me just turn on the audio and make sure we're going there. Lower the music a little bit. I want like the subtle music, but not too strong. Okay. Okay, so here's the game setup. And we had these 3 players go first, and I'm the 4th player in red. And now I get to choose where I want to place my my settlement and my road. So we'll go ahead and close this, and I'm going to put my settlement and road here. Click check, and I'll build a road that way. And it's my turn again. So I'm going to put my settlement here. And I'm going to build my road this way. So now it's Marianne's turn, and what's going to happen? They're going to roll, or actually they're going to put their resources. We'll start rolling once the rounds start again. Everyone's putting their second settlement, their second road. All right. And now somebody rolled a 1 and a 5, which means it equals 6. And then those numbers give the resources to the players. Someone's asking to trade. I'm just going to say no to the trades right now so we can go through a few rounds so you can see how the probabilities of these are showing up. So somebody rolled an 8. So people are getting 8 resources. It's Marianne's turn. They rolled a 9. So they're getting their resources. And now it's my turn. And I'm going to go ahead and roll my dice. And here I got a 4. So anyone on a 4 gets their resources. Now, for the mechanics of this game, I just want us to focus on the probability distribution. So you might be asking, how does that look? So I'm going to click on this dice statistics. And here it's going to show us for the whole game what the dice, which dice have been rolled. Now, note that we have 4 players and they've each gone once. So we've had a total of 4 die roll, which you'll see here. And now what we're interested in knowing is how many times did the number show up. So in this case, the number 4, the number 6, or the combination, I should say, the combination 4, 6, 8, and 9 have showed up at least once. So I'm going to go ahead and close the dice statistics, and I'll end my turn. And I'm going to play through this really quickly so that you can see that as the dice are rolling, what we're going to generate in as dice statistics are a probability distribution that should look very similar to the pyramid that the dice statistics. Okay, so it's my turn. I can take a moment to take a break and look at the dice statistics. And what you'll see here in the bottom left corner is now for the whole game, we'll see that there are a total of 16 dice that have been rolled. So we've gone 4 rounds and each player has rolled once. So it's 4 times 4 is 16. And we'll see here the maximum number of rolls of a particular dice is 4 in this case. And what you'll see here is the slight pyramid that we observed earlier. Now, if we play this game for 4 more rounds, up to like 30 to 50 rounds is typical for this game. What you'll see is that the instances of the dice look like the pyramid, right? So if you keep repeating a die roll, or in this case, 2 die roll, and adding the combination of the 2 numbers on the die that show up, what you'll see is that in as over time or with more and more die rolls, you'll start to see that distribution form. And this is what we call probability, right? And probability distribution. So even though we're playing a game and it's fun and exciting, know that there's a mathematics that are underlying what's going on here. So with that, I'm going to go ahead and jump back to the PowerPoint, and I'll put the screenshot here of the game board by the end of the last round and the distribution. So the big question is, how does this relate to political science? Well, in political science, we're interested in political actors, institutions, behaviors, and we're interested in how one thing affects the other. Now, one thing that we are challenged with in political science is knowing if one thing causes another thing. And so one way that we try to explain it is theoretically, like this will cause that, and we explain why that would occur. We also would collect data, and with the data showing a relationship between 1 and 2 things, what we do is then use statistics and more advanced statistics to try to see what the effect of, let's say, a political actor has on a political institution. And in using those statistics, part of the underlying mathematics is randomness and probability, particularly. And if we know the probability of something occurring, we can start to say, well, what's the instance? What's the likelihood of us seeing that, given the distribution of events? So we can use mathematics to say, given our empirical analysis or our statistical analysis, we can then say with some level of I won't say certainty, but with some level of accuracy or viewing that it's possible that this relationship actually does exist, and one thing may cause the other with some level of probability. And so I just bring this here to political science because this is one of the things that we're challenged with, right? In our world, we don't really do experiments like on cells or on mechanics or on atoms and other things. Like we work with people, we work with societies, we work with governments, and by their nature, they're you can't experiment with them. So you have to then use other tools to try to generate that relationship and to explain that one thing may cause the other. So go ahead and end the recording and get to the discussion. Thanks for taking the time to watch, and hopefully this is a fair introduction to the notions of randomness and probability, and just keep this in mind as you're going forward. So take care, and thanks for your time.